ensuring consistency and scalability in Java Spring Boot microservices architecture. Ensuring consistency and scalability in Java Spring Boot microservices architecture. To reduce fragmentation, we published a reusable Spring Boot starter project that all teams inherited. This included standardized project structure, dependency management, and lifecycle hooks. Logging, security, and exception handling were all abstracted into shared libraries to avoid reimplementation. All APIs had Open API YAML definitions, which enabled front-end teams to auto-generate clients and test contracts early. SonarQube was integrated into every pipeline, blocking PRs that didn't meet code coverage and complexity thresholds. This ensured consistent code quality across services. We enforced architectural patterns like layered service design and avoided tight coupling of controller and persistence logic. We used Consul as our service registry so services could auto-discover one another based on tags and health status. Feign clients, annotated interfaces, provided clean and declarative service-to-service calls, improving readability and testability. Kafka was used for all event-based workflows like logging, audit trails, and asynchronous user notifications, minimizing blocking HTTP calls. Authentication was stateless. Services validated JWT tokens on each call and extracted roles claims to enforce RBAC. Circuit breakers, retries, and timeouts were configured per client using Resilience 4J to isolate failures and prevent cascading outages. Each service was packaged into a Docker image with environment variables injected at runtime, no hard-coded config or secrets. We deployed on AWS EKS, with every service managed as a Kubernetes deployment object, ensuring self-healing and isolated rollback. PAs were defined with resource thresholds and min-max replica counts, allowing services to auto-scale under load. Helm charts were maintained per environment, including secrets, config maps, and auto-scaling settings, promoting config as code. We layered in Jinx ingress controller and Istio mesh to handle internal routing, secure MTLS communication, and traffic shaping. Fluent captured structured JSON logs from each container and shipped them to Elasticsearch, enabling centralized search in Kibana. Prometheus scraped actuator Prometheus endpoints and exported key service metrics such as request counts, latencies, and error rates. OpenTelemetry provided end-to-end trace data, correlated via Jaeger, allowing us to track cross-service request flows and diagnose latency sources. We set SLOs for services and configured alerting rules via Alert Manager for proactive issue detection. Health probes and readiness checks were used by Kubernetes to control service traffic and prevent failures from reaching users. We documented rules for building services, naming conventions, status code usage, pagination, error formats, so APIs looked and behaved the same across the board. The DevX portal allowed engineers to bootstrap new services in minutes, with pre-wired code for logging, metrics, error handling, and unit test scaffolding. API versions were explicitly tracked using URI versioning, not headers, to keep backward compatibility and simplify gateway routing. We mandated secure coding guidelines, static code analysis, and stride-based threat modeling as part of our secure SDLC practices.